All right, guys, we're going to go over section 13.3, energy in simple harmonic motion. Not a whole lot of new ideas in this one. It's just how we apply it. So the notes are pretty small. We'll go over several examples in the next videos. All right, so we're going to apply this formula for horizontal springs with no friction. That would be something that would like this, oscillating back and forth, free of any frictional forces. So imagine a system like this. So if you remember back to energy, just a plain old E represents total mechanical energy, which at any given moment is a total of kinetic plus potential. So if we have something as a horizontal oscillating object on a spring, the only energies involved are, of course, kinetic because it's in motion, and no gravitational potential, but spring or elastic potential. So that's why we have the 1/2 kx squared in there. And it turns out that at any given moment, if you add those two together, yes, that's a total mechanical energy, but it'll always equal 1/2 times the spring constant k times the square amplitude. And as long as there's no friction, that value is constant at that of the total mechanical energy at any given time. A common thing asked to find using this formula, and this formula makes it pretty easy to find, is to calculate the maximum velocity. Well, the maximum velocity, let's flip it to the simulation, occurs when we have the least potential. When we have the least potential, that would be when the spring passes through the equilibrium position. So the most potential are at the greatest compressions and stretching, or the endpoints of this right now. There and there have the most potential. So somewhere in the middle of that, in the exact middle, would be the equilibrium position of the spring, about where I have the cursor right now. That would be where kinetic is at its greatest, halfway between its max stretch and max compression. And since that's the case, we could set the position x equals 0. That means it's not stretch and compressed. If we plug that in to the equation above, it gets rid of this whole term because there's no potential position. If we then solve for V, that becomes the V max because it's at its highest kinetic energy, and it yields this formula from the equation above, square root of k over m to amplitude A. But if you remember back to early in the chapter, there's another way we could write it. Since the square root of k over m equals angular velocity omega, we could also write it in this form. Now, in the next two videos, we'll be going examples of in this section based on this idea.